By the time you finish watching this, a neural network will have written a poem, diagnosed a disease, and made a stock trade faster than you blink. And it doesn't think at all. Hook_end. That's the first thing you need to unlearn. Neural networks aren't brains. They're not even close. They're just math. Really, really good math. That we've tricked into looking like magic. And once you see how the trick works, you'll never look at AI the same way again. Pattern_interrupt. Let's start with why this matters right now. Every time you unlock your phone with your face, or Google shows you a perfect search result, or Netflix recommends a show you actually want to watch, that's a neural network. But here's the thing. 5 years ago, these systems were laughably bad. Today, they're writing college essays and passing medical exams. CLIFFHANGER. So what changed? It wasn't a single genius breakthrough. It was 3 things coming together. More data, faster computers, and a dirty little secret about how we train these things. Let's unpack that secret. Pattern_interrupt. Act 1. The illusion of intelligence. Imagine you're trying to teach a child what a cat is. You point at a cat, say, cat, and eventually, they get it. A neural network does something similar. But it's more like teaching a blindfolded person to catch a ball by shouting, hot, and cold. Pattern_interrupt. Here's the fundamental insight. A neural network is just a giant list of numbers, called weights, that get multiplied and added together billions of times. When you show it a picture, those numbers transform the image into a prediction. This is a cat, or this is not a cat. But initially, those numbers are random. So the prediction is wrong. Embarrassingly wrong. CLIFFHANGER. And that's where the magic begins. Because being wrong is actually how it learns. Pattern_interrupt. Act 2. The mechanics. Let's start from absolute zero. A neural network has layers. Input layer, hidden layers, output layer. Each layer is made of nodes. Think of them as tiny calculators. Each node takes numbers from the previous layer, multiplies them by its weights, adds them up, and then applies a little mathematical twist called an activation function. Pattern_interrupt. That activation function is critical. Without it, the whole network would just be a boring linear equation. You could never learn anything complex. The activation function introduces non-linearity. It's like adding a curve to a straight line. Suddenly, the network can draw circles, spirals, and all the weird shapes that real-world data requires. Pattern_interrupt. But here's where it gets wild. A single node is useless. But stack thousands of them in layers, and something emergent happens. The first layer learns simple patterns. Edges, corners, bright spots. The next layer combines those into shapes. Circles, lines, textures. Deeper layers combine shapes into objects. Eyes, wheels, letters. The deepest layers combine objects into concepts. Faces, cars, words. CLIFFHANGER. This is called hierarchical feature learning. And it's the reason deep learning works. But how do the weights get from random garbage to perfect cat detector? That's the dirty little secret. Pattern_interrupt. It's called backpropagation. And it's actually kind of beautiful. Imagine you're standing on a dark mountain, trying to find the lowest valley. You can't see anything, but you can feel the slope beneath your feet. You take a step downhill. If the slope gets steeper, you're going the right way. If it gets shallower, You adjust. Pattern_interrupt. Backpropagation is exactly that. But in a 10,000-dimensional space. The network makes a prediction, compares it to the right answer, and then calculates a number called the loss. How wrong it was. Then it works backwards through every weight, asking, if I wiggle this weight a tiny bit, does the loss go up or down? If down, it adjusts that weight in that direction. Pattern_interrupt. Do this billions of times across millions of examples. And the network slowly, painfully, finds a set of weights that works. This is called gradient descent. And it's why training a neural network can take weeks and cost millions in electricity. CLIFFHANGER. But here's the punchline. Once it's trained, the actual thinking, the forward pass, is nearly instant. That's why ChatGPT can write a sonnet in half a second. It's not thinking. It's just running the numbers it already learned. Pattern_interrupt. Act 3. Real-world examples. Let's make this concrete. In medicine, neural networks can now detect diabetic retinopathy from eye scans better than human specialists. They don't see the image. They just process pixel values through their trained weights. But the result is the same. A diagnosis in seconds that used to take hours. Pattern_interrupt. In translation, systems like DeepL use transformers, a type of neural network that pays attention to which parts of a sentence matter most. It doesn't understand Japanese, but it has learned patterns so well that it can output fluent French. The entire translation happens in a single forward pass. No thinking required. Pattern_interrupt. In autonomous driving, neural networks process camera feeds in real time to identify pedestrians, traffic lights, and lane markings. They don't know what a stop sign is. They just know that certain pixel patterns correspond to brake now. And they do it faster than you can blink. CLIFFHANGER. But here's the uncomfortable truth. These systems are brittle. Change one pixel, literally one pixel, and a cat becomes a toaster. That's called an adversarial example. And it reveals that neural networks don't understand anything. They're just pattern matching machines on steroids. Pattern_interrupt. Act 4. The implications. So what does this mean for you? If you're worried about job replacement, here's the honest take. Any job that involves repetitive pattern recognition is at risk. Radiology, translation, data entry, even some legal work. But anything that requires causal reasoning, common sense, or physical interaction with the world, that's safe for now. Pattern_interrupt. Because neural networks have a fundamental flaw. They can't learn causality. They see correlation everywhere. If the training data shows that people who wear glasses tend to be smarter, the network will learn glasses equals smart. It has no way to understand that glasses don't cause intelligence. It just sees patterns. CLIFFHANGER. And this is the biggest risk. When we let these systems make decisions about loans, hiring, or criminal sentencing, they encode the biases in their training data. Not because they're malicious, but because they're just math. And math doesn't know it's being unfair. Pattern_interrupt. Act 5. The future. So where are we going? The next frontier is called self-supervised learning. Instead of needing millions of labeled examples, networks are starting to learn from raw data. Like a child watching the world. Models like GPT-4 and Gemini are already doing this. Absorbing the entire internet without explicit labels. Pattern underscore interrupt. The result is systems that can generalize better, handle ambiguity, and even show glimmers of common sense. But let's be clear. They're still just giant pattern matchers. They don't have consciousness, emotions, or desires. They don't want anything. They just predict the next word or pixel based on what they've seen. Pattern underscore interrupt. And that leads to the most important question of our time. If we build systems that can simulate understanding perfectly, does it matter that they don't actually understand? When a neural network tells you it loves you, is that any different from a human saying it? If the output is identical. CLIFFHANGER. I don't have the answer. But I know that the way we answer that question will shape the next century. Pattern underscore interrupt. So here's my challenge to you. Next time you use an AI tool, remember what's underneath. Not a brain. Not a mind. Just math.